This video is going to cover section 2.5, which is rational expressions and equations. Rational just means fractions. So we're going to simplify rational expressions. We're going to combine rational expressions using addition, subtraction, multiplication, and division. We're going to simplify complex rational expressions, and we're going to solve rational equations and work on some work rate problems. So let's first talk about simplifying rational expressions. A rational expression is simplified when all the common factors are removed from the numerator and denominator. To do this, you have to factor the rational expression first. You need to know the difference between factors and terms. So in this rational expression here, we've got two terms in the numerator, a 5x and a 15. We've got a single term in the denominator, a 5. We cannot cancel out the 5 in the 5x and the 5 in the denominator because we would be forgetting the fact that that 15 also needs to be divided by 5. So before we can cancel out the common factors, we have to factor the numerator. Okay, so now we factor the numerator and we see that there's a factor of 5 in all the terms of the numerator. Now that we're completely factored, we can cancel out those common factors of 5 in the numerator and denominator. Okay, so that's simplifying rational expressions. You've probably done this before. Let's talk about adding rational expressions. When we add rational expressions, we need to find the common denominator, meaning the denominator that is common to all of our fractions, and multiply each fraction by some version of 1 in order to rewrite that fraction as an equivalent fraction now with this common denominator. Then you can add or subtract the numerators over that same denominator and simplify. So in this example, we've got two fractions. Our denominators are 10x squared and 25x. So we see that the common denominator is going to be, what is it going to be? It's going to be, there we go. Our common denominator is going to be 50x squared. You don't even actually have to know that our common denominator is 50x squared. Basically, what you need to do is look at your first denominator and look at your second denominator and ask yourself, what factors are my first denominator missing that my second denominator has? That factor of 5, okay? Then say, what is my second denominator missing that my first factor has? Well, my first fraction has a factor of 2 and an extra factor of x. So we just need to give our denominators all the pieces that they're missing to make them identical, okay? And in doing this, we are just multiplying by versions of 1, because whatever we multiply the denominator by, we have to multiply the numerator by, so that we don't change the value of our fraction. We just change the way it looks. Okay, so here we're going to multiply our first fraction by 5 over 5 and our second fraction by 2x over 2x. And now both our fractions have denominators of 50x squared. The new numerator for our first fraction becomes 15. The new numerator for our second fraction becomes 14x. And once we have the same denominator, we can combine them as one fraction. The denominator is the same because that tells us the size of our pieces. The numerator we add together, that tells us how many pieces of that size we have. In this case, it's already simplified, so we are done. Let's do this other example with subtraction. So here, denominators have multiple terms, which means if we want to see what factors our denominator have, we're going to have to factor them first. So x squared minus 4 is a binomial. So it factors as a difference of squares, x plus 2 to x minus 2. The x plus 2 does not factor. So it in itself is a single factor. So x plus 2 is all one factor in the denominator there. And so now we can look and we can say, well, our common denominator is going to have a factor of x plus 2, and it's going to have a factor of x minus 2. So our second fraction needs a factor of x minus 2. Be very careful when you have multiple terms with your fractions. Remember, the fraction bar is a grouping symbol, and so it's a good idea to just put parentheses around everything in the numerator and everything in the denominator before you combine with other fractions. Okay. So we're going to multiply by this version of 1, x minus 2 over x minus 2. Now our denominators are the same. We have to distribute that 3 to the x and that 3 to the, we do 3 times x and 3 times negative 2. But remember, this whole thing is being subtracted. So we're going to end up with a 3x and a negative 6, but we are subtracting all of that. So we are going to subtract this negative 6, which gives us the positive 6. Okay, we're also subtracting the 3x. So 6x minus 3x gives us a positive 3x. You might want to just work through this from right here to make sure you get a 3x plus 6 and really understand why there is a plus 6 there, not a minus 6. This is a super common mistake that a lot of people make, and it can really mess you up further down the road. So really make sure you are distributing that that subtraction sign all the way through and getting the correct sign in your final answer. About multiplying and dividing. When you multiply fractions, you multiply just straight across. Do remember to use parentheses around your numerator and denominator and the distributive property. When we divide fractions, we take the reciprocal of the fraction we're dividing by, and we turn it into multiplication. Okay, that's because multiplication is the inverse of division, and a reciprocal is the inverse of that fraction. Okay, so it's basically a double negative to divide fractions. Simplify when you're done. So let's go through the first example, multiplication. We've got a x squared plus 3x minus 10 over x plus 3 times x minus 3 over x squared minus x minus 2. We begin by factoring both numerator and denominator. And the reason for that is, if we distribute first and do the full multiplication, then we're going to have to factor it anyways and kind of reverse the multiplication distributive property in order to cancel any common denominators. So we factor first, and if you want to, you can really see this as all one fraction at this point in time, right? You can connect this fraction bar, put parentheses around the x minus 3 and the x plus 3, and just see this as all one fraction, okay? Really, to multiply these two fractions, we just need the parentheses and to combine it into one fraction. And then we've multiplied it, we just haven't simplified it. So we factor. We see that we've got some common factors here, and we can cancel out those common factors. Okay. And then we end up with our fraction, which is already factored. So we know that we don't have any common factors. If you want, you can multiply this through, or you can leave it in factored form. Let's do a division problem. So first, we're going to take the reciprocal and make it multiplication. Okay. Now we do the same process as we did before. Things are already in factored form, so we can just combine it as one fraction and ask ourselves if there's any common factors we want to eliminate. We've got a common factor of 3, a common factor of x, and a common factor of x minus 2, and we can simplify that. All right, so that's multiplying and dividing fractions. It's really all just multiplying fractions and simplifying. Don't forget to use your parentheses. Use parentheses, overuse parentheses, and watch out for negative signs that need distributed through. All right, now let's talk about complex fractions. So we're going to take all the tools we know about simplifying our fractions and multiplying by versions of one and use that to simplify complex fractions. So a complex fraction is a fraction with one or more fractions in the numerator or the denominator. Essentially, a complex fraction is when we have fractions inside of other fractions. A complex fraction is simplified when the numerator and the denominator don't contain fractions inside of them. So we only have one main fraction bar, okay? And then they're also simplified when they share no common factors, just like how we simplified regular fractions. So for example, the complex fraction, x plus 1/2, all divided by x plus 1, simplifies to 2x plus 1 over 2x plus 2. And I will show you how we do this. But just notice that that first fraction is complex because there's a fraction inside of a fraction, and that second fraction is simplified because it does not contain interior fractions. And also, take a moment. If you're thinking, wait, what about the factor of 2 here? Think again. The numerator does not contain a factor of 2. The numerator's first term has a factor of 2, but 2 is not a factor of the entire numerator because this one does not contain a factor of 2. So the only factor in the numerator is 2x plus 1. That is a full factor. It cannot be factored any further. And so for that reason, we cannot cancel a factor of 2 out of the numerator and the denominator because the numerator does not contain a factor of 2. Its term contains a factor of 2, but not the other term. So before I go into showing you how they do this, let me explain the two different methods. So we've got two methods to simplify complex fractions. The first method is going to use division. Here we numerator and all its interior fractions, and we add those together to make a single fraction in the numerator. And same thing with the denominator. We turn the denominator into one single fraction. Then we divide over the main fraction bar, because remember that main fraction bar really means division. Once we do that, we will get a fraction that is not complex. The other method is to cancel out the denominators of our interior fractions using the LCD. So we're going to multiply a version of 1, which is the LCD over LCD, and we multiply over the main fraction bar. And in doing this, we are going to cancel the denominators of our interior fractions. Let me show you both methods and show you when is a good idea to use each. So example that we just had, x plus 1/2 over x plus 1. I'm going to go through the first method. So the first method wants us to turn the numerator into a single fraction. So we've got an x plus a 1/2 in the numerator. We need to add those together so it's a single fraction. Okay. To do that, we find the common denominator. And remember, we're just looking at this x plus 1/2 piece. Common denominator is 2. So we say that's 2x over 2, and we can add them together. So now our numerator is a single fraction, 2x plus 1 all over 2. And our denominator is all a single fraction, x plus 1 over 1. Okay, so we've got a fraction divided by a fraction. We translate that into fraction division, which is really multiplication, which then gives us our 2x plus 1 over 2x plus 2. Right, we're just going to flip this fraction and multiply straight across. So that's method 1, where we do what we need to make the numerator and the denominator each their own fraction. And then we've got a fraction divided by a fraction, and we turn that division into multiplication. Okay, that's method 1, is the division method. Now method 2, we're going to find the LCD of our interior fractions and multiply the main fraction by LCD over LCD. So in this case, we only have a single interior fraction, this 1/2. Its denominator is 2. So our LCD is going to be 2, So we need to multiply across the main fraction bar by 2 over 2. That means we are multiplying x plus 1/2 times 2. So we have to distribute the 2 to both of those terms. And we are multiplying x plus 1 times 2. So we have to distribute the 2 to both of those terms. Notice what happens. When we distribute that 2, it will cancel out with our denominator. That's why we're multiplying by the LCD in the top and the bottom, is to cancel out the denominator of our interior fractions here. We simplify that stuff and we get 2x plus 1 over 2x plus 2. So both methods get us to the same end. In this case, the first method took a little more work than the second method. Both methods always work. It depends what you're more comfortable with. You do need to be very careful when multiplying by these fractions, that you understand what's going in the numerator and what's going in the denominator. So this 2 in the denominator is multiplying the entire denominator. This 2 in the numerator is multiplying the entire numerator. So see how I distributed the 2 to the x and the 2 times the 1/2? This green 2 goes in the numerator of the numerator, okay? So be careful to just understand where things are getting multiplied to, whether they're in the numerators or the denominators, okay? Now I'm going to show you using 2 examples when you should use each example, when you should use each technique. So first of all, if your numerator and your denominator are already single fractions, then it's a good idea to just go straight to the division method, because I won't have to do any fraction addition here. I can just go straight to 5x over x plus 2 divided by 10 over x minus 2. Okay, so that's when it's easy to use the division method. Now, if your numerator and denominator both contain multiple fraction terms that would be a pain in the butt to have to add together already, using the LCD is a good way to go. So let me work you through both of these examples. Okay, so our first example, we are going to use the division method because it's really already set up for us. Divided by a fraction. So we'll rewrite it as 5x over x plus 2 is being divided by 10 over x minus 2. This is the same thing as 5x over x plus 2 being multiplied by x minus 2 over 10. Okay. Now we just multiply straight across, but remember, this is a grouping. This is a grouping. So we're going to have to use the distributive property. So we're going to get 5x squared. Well, actually, let's just multiply straight across without multiplying it out, because we're going to have to factor anyways, aren't we? There we go. So we've got 5 times x minus 2 and 10 times x plus 2. We have a common factor of 5 here because we are in factored form. So we can cancel out that common factor of 5, and we're going to be left with a 2. So our answer is going to be x times x minus 2 over 2 times x plus 2. All right. Everything looks really similar, but there are no common factors here. That is our answer. So see how, because we were already set up to do fraction division, that's the easiest way to go in this scenario. Let's take a look at our next example, and I'll show you the LCD method and why it's nice here. Okay, so in this example, if we wanted to use the division method, I would have to first find an LCD and add both these fractions. Then I have to find an LCD and add both these fractions. Then I do division. But since I'm gonna have to find an LCD for these and an LCD for these, why don't I just find an LCD for all 4 of these denominators and multiply by it? So our denominators are, our interior denominators are these 4 guys. So our LCD is y squared x squared, okay? So now I'm gonna multiply the main fraction bar by y squared x squared over y squared x squared. All right. Some people like to do y squared x squared over 1 over y squared x squared over 1, just so you can see how stuff lines up. So this fraction bar lines up with this fraction bar lines up with that fraction bar, okay? But you really don't need that over 1 piece. Right. So now let's distribute everything out. We've got x over y squared times y squared x squared plus 1 over y times y squared x squared. That's our numerator. And our denominator is y over x squared times y squared x squared plus 1 over x times y squared x squared. So notice how this numerator goes into the numerator of the numerators, and denominator goes to the numerator of the denominators. Okay. Now we can cancel stuff out. So the y squared here cancels with the y squared here. The y cancels with one of these y's. The x squared cancels with this x squared. And this x cancels with one of these x's, right? We specifically multiplied by a version of 1 that gives us LCD over LCD, so that we will definitely cancel out each of these denominators, because we know that y squared x squared is a multiple of every single one of these denominators. So now we've canceled out all our denominators. Let's regroup with what we have left. We've got an x times an x squared up here. X times x squared is going to give us x to the 3rd plus a 1 times x squared. So that's our new numerator. And the denominator has a y times y squared, so y to the 3rd, and a y squared x. All right, so that is our new denominator. If we want, we can see what we've got left and see if we can factor this guy. Oh, it looks like I'm missing a little piece. This y is still there. Okay, so we've got x to the 3rd plus x squared y over y to the 3rd plus y squared x. We've totally dealt with our complex fraction. Let's make sure we deal with simplifying. All right, so here's our fraction in the numerator. We can factor out an x squared, and we're left with an x plus y. In the denominator, we can factor out a y squared, and we are left with a y plus x. Well, x plus y and y plus x are the same things, and we're in factored form. We can cancel them out. So that whole fraction simplifies to x squared over y squared. All right, so that's using the LCD method. Both methods will always work, but the LCD method it is a nice way to go when you have so many fractions. Okay, now let's talk about simplifying expressions that have negative exponents in them. So to simplify expressions with negative exponents, we need to get rid of negative exponents and then simplify whatever fractions are left. We see negative exponents a lot because they come up, but we don't like to report our answer with negative exponents unless we're doing scientific notation or something like that. So keep in mind, x squared means to multiply by x twice. X to the -2 means 1 over x squared, or in other words, divide by x twice. So positive exponents are repeated multiplication, negative exponents are repeated division. Okay. So let's do a simplification. We've got this fraction here that has a bunch of negative exponents inside of it, and we're going to want to simplify it. First, convert your negative exponents into fractions. Remember that your exponents are tiny numbers. They only apply to the factor they are on top of, unless there are parentheses extending them to the other factors. So what I'm saying is this 3x minus 3 times x to the -1, the -1 exponent only applies to the x, right? This -1 does not apply to the 3. So the 3 stays in the numerator, the x goes into the denominator, okay? We can also think about this as 3 times 1 over x, and we do that multiplication, okay? In our second term, we've got 1 over x squared times 1 over y, so that becomes 1 over x squared y. In the denominator, our y to the -2 becomes 1 over y squared. Our x, y to the -1 becomes x over y. Okay. You might ask, when is it okay to just drop this thing into the denominator versus rewriting it as 1 over x? Well, if it's a factor, when we multiply by a factor of 1 over x, the x basically goes into the denominator. So if it's just a factor, we can just drop it into the denominator. But if it's a term and there's lots of additions and subtractions, we have to be very careful that we are keeping our fractions straight. So first step, rewrite your negative exponents as fractions, and be careful that you are applying the exponent to the proper factors and not doing anything you shouldn't be allowed to do because of addition or subtraction getting in the way. Once we do that, we can multiply. In this case, we'll multiply by the LCD, which again is x squared, y squared, and cancel all our denominators to get our new simplified fraction. Okay. It's possible this guy, let's see, we can factor out a y and we can factor out an x. No, they're still going to look different. Okay. So that's simplifying with negative exponents. Basically, translate your negative exponents first, and then you're just simplifying a complex fraction. Okay, let's go on to solving rational equations. I've got a handful of examples here that we're going to go through. Solving rational equations is not too different from solving other equations, except that we are going to still use all the properties of equality, but we're going to use a new technique to get rid of fractions. You don't have to use this technique, but unless you want to be adding and subtracting fractions from both sides, it's a good idea to multiply both sides by the LCD of every fraction in your equation. And that will get rid of the denominators, and then you no longer have fractions, and it's a lot simpler to solve from there. Okay. When solving rational equations, we have to be careful for the situation of dividing by 0. So you want to check your solutions. And if your solution ever makes the denominator of the original equation 0, then it's not a solution. Okay. Let's start with our first example. Let me move to the whiteboard. All right, so our first example, x plus 5 over 2 equals x over 7. You may look at this and say, oh, we should cross multiply. Cross multiplying is actually just a shortcut for multiplying both sides by both denominators. Right, if I multiply both sides by 2 and both sides by 7, the 2 cancels out on the left, 7 cancels out on the right, and we're left with an extra factor of 7 on the left, an extra factor of 2 on the right. Okay. So we're going to multiply both sides by 2 times 7 because our LCD is 14, but I'm going to keep it in factored form so that I can easily cancel out those denominators. Okay. Now what's left is a 7 times x plus 5. And remember, fraction bars are grouping symbols, and a 2 times x. I can distribute that. And then I will subtract 2x from both sides and subtract 35 from both sides. And then divide by 5, we get x is -7. Now, in this case, we didn't have any variables in our denominator, so we don't really have to worry about making the denominator of our original equation 0. Remember, our original equation is the x plus 5 over 2 equals x over 7. But just to be safe, let's check our answer in there. Our answer is -7. So what does this give us? -7 plus 5 is -2 over 2. And -7 over 7 is a -1. -2 over 2 is also -1. So we are good. If x is -7, both sides are equal to each other. That's all we need to check. Let's go on to the next problem. All right, in this equation, we only have one fraction and a handful of different terms. So our LCD is going to be x because the denominator of all the fractions here is either x or 1. So our LCD is x. So we're going to multiply both sides of our equation by x. Remember, multiply both sides in their entirety, use the distributive property. We're going to end up with 3x minus 6 equals x squared plus 8x. It looks like we have a quadratic. So I'm going to move all my terms to the same side. I'm going to have x squared. So I'm going to subtract 3x. And I'm going to add 6. So we've got a quadratic here. If we can factor it, that's usually the easiest way. So I think x, what adds to 5 and multiplies to 6, x plus 2, x plus 3. So we know that x can equal -2 or -3. Then we want to just go back into our equation and be like, if x is -2, is this denominator 0? No, the denominator is -2. If x is -3, is this denominator 0? No, this denominator is -3. So we're good. Let's take a look at our third example. We've got 2x over x minus 4 is equal to 8 over x minus 4 plus 1. All right. We're going to multiply both sides by the LCD. The LCD here is x minus 4. On the left-hand side, it's going to cancel out. We're going to end up with 2x. On the right-hand side, we're going to end up with 8 plus 1 times x minus 4, which is just x minus 4. And we don't need parentheses. Let's simplify by subtracting x from both sides. And we're going to end up with x equals 4. All right, that seems pretty straightforward. Now let's just check if x is 4, does it make the denominator 0 in our original equation? It does. So x cannot equal 4. There is no solution. Okay. So there's no solution to this equation because the solution we found makes the original equation undefined. That's why you have to make sure to check your answers because it seems very simple to say x is 4, but x cannot be 4. It would make the equation undefined. All right, we've got 2 more examples to go through. This one's going to take a little bit of work because we're going to have to do some factoring. All right, so we've got 3 fractions here. If we want to find our LCD, we're going to have to factor our denominators. All right, so first we're going to have to factor our denominators. We see that these 2 fractions are their own factors. Their denominators are single factors of x minus 5 and single factor of x minus 6. Now we want to factor this x squared plus x minus 30. X squared plus x minus 30 is actually going to factor to x minus 5 times x plus 6. And notice that's a plus there and that's a negative there, which is a bummer. Because if this was a negative 6, then this would be our LCD. But now our LCD needs a factor of x minus 6, a factor of x minus 5, and a factor of x plus 6. Okay, so our LCD is going to be x minus 5, x minus 6, and x plus 6. All right, that is the expression that has all the factors of our denominators here. So I'm just going to replace this denominator with this denominator in its factored form. Now we're going to multiply everything by the LCD. All right, so I'm just going to write LCD here. We're multiplying both sides by the LCD and we're distributing it out. Notice that when we multiply our first fraction by the LCD, the x minus 5 and the x plus 6 get canceled out, but we're still going to have an x minus 6. So our first term is going to be 4x times x minus 6. Everything else got canceled out. Our second term, we've got an x minus 5 in the bottom. So when we multiply by the LCD, the x minus 5 will cancel out, but we're still going to have both of these linear factors. So our second term is going to be 2 times x minus 6 times x plus 6. Okay. And then our third term, we've got a factor of x minus 6 in the bottom. So those will cancel out, but we're still going to have the x minus 5 and the x plus 6. Okay, so this is what we're looking at now that we've multiplied by the LCD. Okay. We no longer have fractions, which is great, but we are going to have to multiply through with everything and then add our like terms together. And we are going to end up with the quadratic equation that looks like this. 5x squared minus 25x minus 42 equals 0. And you have a couple choices here. You can complete the square, or you can factor by grouping if possible, or you can use the quadratic formula. I would suggest just using the quadratic formula to solve for x. And I'm not going to go through that because we've already talked a lot about using the quadratic formula. The part here that I want you to see and understand is that we had this big rational equation. We had to factor all our denominators to come up with our LCD, multiply everything by the LCD, which then eliminates the denominators and gives us an equation that we can solve. All right. We have one more equation, and that is this. Now here we have multiple variables, but we are asked to solve for x. So we will use the same process that we did before. Multiply everything by the LCD. In this case, our LCD is a, b, x, right? All the factors from all our denominators. When we multiply everything by a, b, x, we are going to end up with bx plus AX equals AB. Now we want to solve for X, so we're going to factor that X out. And then we will just divide by AB, or A plus B. So we get that X equals A times B over A plus B, and we have solved for X. All right. So that's solving rational equations. If you need to go through those examples, please do. Let's now talk about our work rate problems. And our work rate problems are going to actually use this kind of an equation. That's why I wanted to show you how to solve that kind of an equation. All right, so our work rate problem. I'm going to give you an example. If it takes Sam 3 hours to put a desk together, and it takes Adam 7 hours if he were to put the same desk together on his own, how long would it take them if they worked together? Now you have to keep in mind, because they're working together and Sam is so much faster, Sam is going to end up doing a lot more of the work, right? It's not like Sam's just going to work for an hour and a half and Adam's going to work for 3.5 hours, so they each do half the desk. They're both going to work the same amount of time. All right. So these kind of work problems or rate problems have multiple ways to solve them, but an interesting technique I'm going to show you right now, and it's a really fun way to solve these guys. So what we're going to do is break the work done into units of time. So since our units of time are in hours, we're going to say how much work are they each doing in an hour? Like how much of the desk are they each getting put together in the first hour? So in the first hour, Sam's going to get 1/3 of the desk completed, right? Because he can do the whole desk in 3 hours, so he's getting 1/3 of the desk done in the first hour. Now in the same hour, they're working together, Adam's going to get 1/7 of the desk completed because it takes him 7 hours to do the desk. So together in the first hour, Sam's going to get 1/3 of the desk done. Adam's going to get 1/7 of the desk done. So if we add those two fractions together, it will give us the fraction of the desk completed in the first hour. Okay. Well, if we want to know the total hours it takes them to put this desk together, it's going to be in the first hour, they're going to get 1 divided by the total hours it takes them. They're going to get that fraction of the desk completed. So we can actually set up the equation 1/3 plus 1/7 equals 1/x, where x is the hours it takes them to put the desk together, right? Because in the first, let's say it takes them 20 hours to put the desk together together. Then if they work for an hour, they're going to get 1/20 of the desk done. So that's where this x comes in. X is the total hours, but the fraction of the desk that they get completed in the first hour is going to be 1/x. So we can set up our equation 1/3 plus 1/7 equals 1/x, where x is the total hours it will take them if they work together. And we can just solve this equation like our regular LCD. Multiply by 3 times 7 times x, cancel out our denominators, and we get that together it takes them just over 2 hours, which really makes sense. Because it takes Adam over twice as long to help Sam. So Sam's really doing a lot more of the work here in this 2 hours. Okay. So that's how we do work rate problems. It's this idea that we break the work done into units of time. So everything is going to be 1 over total hours. And so that our equation is based on how much work gets done in 1 hour. Okay. So that is section 2.5. There was a lot of stuff here, so take your time, go back through it, pause where you need to, and let me know if you have questions. Good luck.